Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. In the Module 6, we are studying about aldehydes and ketones. In the last lectures, we will be studying about worked out examples related to aldehydes and ketone. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by TTH Swayamprabha, MHRD, New Delhi. So in this particular session, we will be studying about a few of the worked out examples related to aldehydes and ketones. We will be dealing with a couple of reactions, how to solve the reactions and how to identify the product from various reactions and the reagents and the conditions. Let us welcome to the next session. In this particular session, we will be working out some problems related to aldehydes and ketones. So the first question is identify the product formed in the following reaction. So we have a aldehyde that is treated with a 10% sodium hydroxide. So we need to identify what is the product that is formed in this particular reaction. So some of the things we have to understand first is this is a basic condition. So hydroxide minus ion is a strong nucleophile as well as base, so that is used in this reaction. And we have a aldehyde. The aldehyde is having a alpha hydrogen. So these are some of the clues given in this reaction. So based on that, we will have to identify how the reaction actually proceeds. So this OH minus is a base, can abstract a proton from this acidic hydrogen on this particular carbon, which is alpha to the carbonyl group. This is electron withdrawing. So this proton is highly acidic. So this acidic proton is abstracted by the base, which generates an anion on this carbon. So this anion can now attack the electrophilic carbon atom on the other aldehyde molecule. So the bond is shifted towards the oxygen. That leads to a condensed product as shown here. So we have this CH2 is attached here. This CH2 is attached to the aldehydic carbon. So this is the carbon where this is added. So this gets the minus charge, and we also added a proton here. So that directly gives a aldehyde and an alcohol. So this is basically the aldol product is formed in this particular reaction. So this is having an aldehyde unit, this is having a hydroxyl unit. So this is a aldol. So aldehyde and alcohol is present in the same molecule. So this is what is called the aldol product. So this is having an alpha hydrogen. So that is very important, and we are using a base. So any reaction in which we are using a strong base and the carbonyl compound has alpha proton, that will undergo aldol condensation. If it is a ketone, then ketone will be formed. And in the next reaction, we need to identify what is the product formed. So we have a carbonyl compound, we have another carbonyl compound. This is nothing but the formaldehyde. This is a cyclopentanone. So like the previous one, here only this compound has the alpha hydrogen. This does not have a alpha hydrogen. So the reaction is going to be a little bit different. So in this particular case, the acidic proton is subtracted from this cyclopentanone derivative. So the anion is formed on this particular cyclopentanone derivative. This minus charge now attacks the aldehydic or the electrophilic carbon atom on the aldehyde, and the bonds are shifted, the bonded electrons are shifted towards the most electronegative oxygen. So this leads to the condensed product, and this on heating undergoes elimination of water molecule to produce this particular compound. So this is having a double bond, single bond, double bond combination. So this is an alpha beta unsaturated system. And now what are the next question is, what are the products formed in the following reaction? We have a dialdehyde. This is treated with a strong base again, potassium hydroxide, in methanol and heated. So we need to identify what is the product that will be formed in this particular reaction. So there are two places, 1 and 2 place. Both this is a symmetrical aldehyde. So we have the same, either the proton is abstracted from this carbon or this carbon, we still end up with the same anion is formed. So this anion is formed in the first step by the base abstraction of a proton. So this negative charge can attack the electrophilic carbon, and the bond is shifted towards the oxygen as shown here, because this is more electronegative. And we do need to cyclize this product, because this is an intramolecular one, that is, the reaction happens within the molecule. So we have to identify how or what is the size of the ring that is going to be formed. So this carbon is, I am numbering it as the beginning carbon as number 1, 2, 3, 4, 5. So there are 5 carbons present in this particular cyclization. So that leads to a 5-membered ring as shown here. And in the first carbon we have the aldehyde unit. So in this first carbon we have the aldehyde unit, and in the 5th carbon we have the OH unit. And if we start from here, 1, 2, 3, 4, 5, and at the 5th carbon we have the O minus. So this is how you have to be very careful when you are doing an intramolecular cyclization, because the number of carbon atoms has to match exactly. We cannot add or remove carbon atoms in these kind of reactions. So a proton is added to this intermediate, and we get the hydroxy derivative. Hydroxyaldehyde is formed. This is nothing but the aldol. This is the intramolecular aldol reaction that is formed in this particular case. And in the second step, what we have is heating is there. So that means this molecule will lose water molecule. Now we have to find out how it will lose the water molecule. So there is a proton here, because the hydroxyl has in the alpha carbon there is one proton here, and we also have another proton here. So there is a competition now between the proton A and the proton B. So whether both will be removed or one only will be removed, we have to identify now. So let us do the removal of water molecule. So we have a compound as shown here. This is the alpha beta unsaturated system. And we have another system which is not a conjugated one, because here a double bond, single bond, single bond, double bond. So this is not a conjugated system. Here we have a double bond, single bond, double bond. This is a conjugated system. So due to the formation of the conjugated product, this compound is formed, whereas this is not formed. So in other words, the proton is removed from A and not as shown in the B. So this is how we have to identify the product in these kind of reactions. So the crucial part for this reaction is the formation of the conjugated product. So as we know, this is the intramolecular aldol reaction which has the alpha hydrogen. So the next one is, what reaction happens when benzaldehyde is treated with this 1, 2, 3 carbon fragment, that is propionaldehyde. So we have two aldehydes. This aldehyde is having an alpha hydrogen. This aldehyde is not having an alpha hydrogen. So the alpha hydrogen one can easily be abstracted by the proton, but this proton can be easily abstracted by the base. So an anion is generated on this particular propionaldehyde substrate. So an anion is generated here. This anion can now attack the electrophilic carbon on the other unit, that is the benzaldehyde unit. So this minus charge attacks here and this bond is shifted towards the oxygen. So we end up with this product is formed. This is nothing but again, if it is a hydroxy derivative, this is the aldol reaction that is formed in this particular case, and this leads to the hydroxy derivative. This gets a proton and gets converted to the hydroxyaldehyde. This on heating obviously leads to the elimination of water molecule. In this particular case, there is only one proton here, so that is the only proton which can be removed. So this leads to extension of conjugation with the aromatic system. So this is the most stable product, and this is found very readily. So whenever we have to solve this kind of problem, what we have to look for is whether the compound or the starting material has the alpha hydrogen or it doesn't have an alpha hydrogen. Based on that, we can decide which type of reaction will be formed. So when this aldehyde is treated with 50% sodium hydroxide, what will be formed? So here there is no alpha hydrogen, so this will undergo only Cannizzaro reaction. So this is the hint we can get. In the previous case, there is alpha hydrogen. So whenever there is an alpha hydrogen and a base is used, that always will prefer to go via the aldol condensation route. When there is no alpha hydrogen, then it will follow the Cannizzaro reaction route. And in the aldol reaction, we use a very less concentrated base, around 10 to 20% of the base can be used. And for the Cannizzaro reaction, we use a very strong base, which is 50% of sodium hydroxide solution. So one of the aldehyde undergoes a reduction and the other aldehyde part undergoes oxidation. So we end up with this particular product. So next, when this ketone is treated with an amine, what is going to be the product under acidic conditions? The last step is the workup with acidic water workup. So we need to identify what is the product formed when these two substrates are reacted together. So what is the hint given is this compound contains alpha hydrogen. So there is an alpha hydrogen present in this one, and this is a secondary amine. So when a carbonyl compound with alpha hydrogen is present and the secondary amine is treated together, we end up with a enamine. So this is the one you have to remember. So how the reaction actually proceeds, we will see step by step mechanism. So this nucleophilic or the basic nitrogen has lone pair of electrons. So this lone pair of electron is shifted to this particular carbonyl unit because this is an electrophilic carbon. So this base or the lone pair electron is shifted to this particular carbon, and this bond is shifted to the oxygen. So what we end up is like there is a plus charge developed on the nitrogen and the negative charge is developed on the oxygen. So there is a bond formed from this nitrogen to this carbon as shown here. And when this abstract proton, because this nitrogen is having electropositive, because nitrogen is more electronegative, so it cannot stay with the plus charge for longer time. So this gains or this removes this proton. The proton is removed from this one, and the removed proton is subtracted by the corresponding O minus. So we end up with the hydroxy, and this becomes a neutral. No charge is on this particular nitrogen. So in this particular step, what happens is like there is the water molecule removal happens, because here we had written like water is eliminated. So the water is eliminated from here, and that leads to the formation of cis and trans product. So this is the enamine that is formed in this particular reaction. So this is a Gilbert-Stock enamine that is formed. This can be prepared very easily from the corresponding alcohol. And the hydroxyl can also be converted to the halo derivative by treatment with the PBr3. And this bromine can be converted to the amino derivative by treatment with ammonia. And the same way the bromine can undergo nucleophilic substitution reaction with cyanide to produce the cyano derivative, which on lithium aluminum hydride reaction gives the amino derivative. And this can also be treated with lithium and copper reagent. So metal cuprate is formed, so that gives the CH2 double bond is added to this particular compound, metal copper reaction. And the next one is this amine can be converted to the dimethyl amino derivative by treatment with methyl iodide. And the carbonyl group can be reduced using zinc and mercury or hydrazine. So both the react conditions can be used to prepare the same cycloalkane in two different ways. And this alkene on reduction with the hydrogen and palladium gives a corresponding ethyl substituted cyclohexane derivative. So that way we can carry out many of these reactions starting from the cyclohexanone. And here we have to propose a mechanism for the following reaction. We have a ester, keto ester is there. This keto ester is treated with methyl magnesium bromide to give a cyclic derivative, that is a lactone. So in the first step, what happens is the methyl magnesium bromide is having a negative charge on the methyl group and a positive charge on the magnesium. So that means this is the nucleophilic part and this is the electrophilic part. So this can easily attack this electrophilic carbon. So the shift of electrons you already are aware of. So this leads to the disubstituted derivative with negative charge on the oxygen. And this oxygen can now undergo, if you look carefully, there is number 1, 2, 3, 4, 5. So 5 atoms are apart from this oxygen to this carbon. So when there is a 5 atoms, so they generally prefer to undergo intramolecular reaction. So that intramolecular reaction leads to this particular derivative. So here we have, starting from the oxygen, 1, 2, 3, 4, 5. So starting from oxygen, we have the first carbon has 2 methyl groups, and this is the oxygen is number 1, 2, 3, 4 and 5. The fifth carbon is having a OAT group and O minus, both are present on the fifth carbon. So that way we can easily draw the structures. And now in the charge reversal step, the negative charge comes between this carbon-oxygen bond and the ethoxide moiety is lost, which leads to the given product as shown here. So this is how we can write a mechanism for this particular reaction. This is an intramolecular reaction. So next we have to find out how we can prepare two different alcohols from this particular cyclohexanone. So here we have a 6 carbon unit, here we have a 5 carbon unit, here we have 6 carbon unit, but it is a 5 plus 1 unit and not a 6 unit directly. So we have to find out how we can synthesize each one. So the first step is the carbonyl compound can be reduced to the hydroxide derivative using lithium aluminum hydride, and we can do the dehydration reaction which produces the cyclohexene. This is having the 6 carbon unit, and this on ozonolysis and zinc and water produces the dialdehyde. So here again 1, 2, 3, 4, 5, 6. So we have to exactly count the number of carbons. Here we start with 6 carbon, so we also end up with the 6 carbon. So this is the dialdehyde that is formed by the ozonolysis reaction. And this on treatment with the sodium hydroxide will undergo aldol condensation. So we have to abstract a proton from the alpha carbon atom. So there is an alpha carbon atom here. So this proton is abstracted by the base. So this intramolecularly attacks this carbonyl carbon, and this particular bond is shifted towards oxygen. So this you are already familiar with. So this leads to the corresponding 5-membered ring, because if you start from here 1, 2, 3, 4, 5. So this is the 5 carbon unit, that is how it is formed. And in one of the carbon, that is the starting carbon, let us say we have an aldehyde. So we have an aldehyde on this carbon, and in the fifth carbon we have a O minus. So that abstracted a proton to give the OH. So that way we can exactly draw the structure of the cyclase product. and this on oxidation produces the corresponding keto derivative, and the aldehyde is also oxidized. So we can do both the oxidation of the primary, the secondary hydroxyl and the aldehyde. So the secondary hydroxyl is oxidized to the ketone, the aldehyde is oxidized to the carboxylic acid, and this on decarboxylation, because this is a, if we say this is a alpha and this is a beta carboxylic acid, this can very readily undergo decarboxylation to produce the cyclopentanone derivative. So this on reduction gives the corresponding alcohol. So starting from the 6-membered one, we ended up with a 5-membered alcohol. So this is how the whole process can be carried out. And from the 6-membered one, we already know how we can reach the 5-membered keto acid. And from this keto acid, when we use the zinc and amalgam reduction, this carbonyl unit is removed, and this on LAH reduction produces the corresponding primary alcohol. So this way the cyclohexanone can also be converted to this particular compound in multiple steps. So now let us find out how we can carry out the following transformation. We have a alkyl unit, that is a cyclopentyl unit with a methyl group, which gives a bicyclic or condensed unit as shown here. So how can we carry out this one? Because the major problem in this reaction is there is no functional group present here and there is no functional group present here. So it is very difficult to carry out reactions on alkyl substitutions or alkanes. It's very difficult. So we have to find out how this reaction can be effected. So the first thing is we have to activate this one, or we have to convert this into a good reactive substance. As we have already seen, the alkyl halides are very reactive species. So this particular alkane is first converted into the corresponding alkyl halide derivative. So the reaction actually produces the most stable bromo derivative on this particular carbon, and this on treatment with the sodium ethoxide produces the elimination product. So we end up with the corresponding eliminated product. This on HBr addition and anti-Markovnikov rule hydrogen peroxide produces this particular bromo derivative. And this bromo derivative on treatment with the magnesium and the ethoxide produces the alkyl Grignard is formed from this particular substrate. And this bromo derivative can also be treated with KOH and water to produce the corresponding hydroxy derivative, and this hydroxy derivative can be oxidized to get the corresponding ketone. So we have a ketone, we have a methyl magnesium bromide, alkyl magnesium bromide. So we have two units of the same, because here we have a 5-membered unit, here we have another 5-membered unit. So that means we have one 5-membered unit here, another 5-membered unit here. So we are more or less having the same pieces which we have to combine together. So these two on when subjected to Grignard reaction and followed by acidic workup produces both these products. So both the products are formed by the Grignard reaction. So in one case what happens is both the methyl group, because we will have a hydroxide derivative, because this one of the carbonyl group, this carbon is converted into a tertiary alcohol, so that tertiary alcohol can undergo elimination. So at that time, whether both the methyl groups are on the same side or they are on the opposite side, we can have two different products. So that is how this Grignard followed by dehydration produces this particular derivative in both the isomeric forms. Let us study the next problem. See, for the preparation of propyl benzene as shown here, the preferred method is a Friedel-Crafts acylation followed by reduction rather than direct Friedel-Crafts alkylation. That is, path B is the preferred one over path A. We need to find out why this is the preferred method. So now to solve this problem, what we need to know is what happens in the Friedel-Crafts alkylation reaction. So in the case of alkylation reaction, that is the path A, if we are using, then the most important thing we have to keep in mind is the rearrangement of propyl cation that is formed in this particular reaction. We already know carbocations are involved in the Friedel-Crafts alkylation reactions. So those carbocation can undergo rearrangement. So that means preparing a N substitute, that is normal alkyl chain substituted benzenes are very difficult to prepare, because if we use this method, what we end up is, along with our required product, that is the N-propyl isomer, we also will get a isopropyl isomer. So the selective formation of N-propyl derivative is very difficult. We will always be having other additional side products like the isopropyl derivative also. So this is one problem. And the next problem is, if the alkyl group is introduced into the aromatic ring, that actually activates this aromatic ring more. In other words, the activation of the aromatic ring leads to polysubstitution, because other than this rearranged product, we may also get polysubstituted like ortho, para, or dry substituted alkyl benzenes are also possible in that particular case. So that is the reason direct alkylation of aromatic systems, basically benzene and other derivatives, are not preferred for the preparation of N-alkyl derivatives. In those kind of cases, what we have to do is, if we do a acylation reaction, that gives only one product, and the presence of this acyl group, that is the ketone, deactivates the aromatic system from any further acylation reaction. So that is how we always will end up with a monoacylated product, and no polyacylations are possible. And then we can simply reduce the carbonyl group to the corresponding alkyl derivative by Wolff-Fechner reduction or other reductions. That gives the alkyl derivatives, N-alkyl derivatives, in a much more better yields. So that is the reason the direct alkylation is not preferred. The path B, where we first carry out the acylation followed by reduction, is the most preferred method for the preparation of N-alkyl derivatives. So in the summary, let us recap. We had studied about various worked out examples related to aldehydes and ketones. We have studied about few conversions of ketones into various derivatives. And we also have studied about the advantage of using Friedel-Crafts acylation reaction over Friedel-Crafts alkylation for preparing linear alkyl benzenes. With this, we conclude this session. Thank you.